Let's go. Hello, everyone. I'm David, coming from France. You can hear this lovely accent, I guess. So yes, the session of the day is about how to search for similar sounds, actually, not musics exactly, even though there is a title. You have my details here, the way to connect to myself, and at the end of the talk, I will share a QR code about everything about the session, so you will have everything. So let's start. Who knows Elasticsearch here? Whoa, a lot of you, cool. For those who don't know, Elasticsearch is based on Apache Lucene. It's an open source project. Apache Lucene is an open source project, and Elasticsearch as well. And it's a means to search for everything, including text, but it could be other kind of data. But for my presentation today, I will introduce a bit more about the text search thing. So you know this movie and this sentence. These are not the droids you are looking for, right? So when you want to index that kind of text and you want to search for it, there is a process happening behind the scene which is called analysis process. So what you do, you basically analyze the text using some filters, and then it's going to transform the text you want to index into something which is meaningful for the inverted index. So what it does, the first step is to remove, for example, the HTML tags that you have here in the sentence, and then produce another set of text. Then you go to a tokenizer. So the responsibility of the tokenizer is to produce tokens. So here it's just split at the spaces and remove the dot at the end. So you have a set of tokens. And then for each token that you have, you go through a filter process. So there are different type of filters built in Lucene and in Elasticsearch. So for example, the lowercase filter is going to lowercase the text. Yeah, easy. And then you have the stop filter, which is going to remove the common words that you have in the English language by default here. So you end up with a droids you looking. And then you can perform some snowball, which is going to take the singular form of the text and the simple form of the verb, if you wish. So at the end, when you are indexing something like these are not the droids you are looking for, you end up indexing droid you look. There's an issue. That was not the drawing I was looking for, but I have indexed the droid I'm looking for, right? This is a totally different meaning here. Same if you want to search for machines instead of droids, then it is not going to work out of the box. You can use synonyms in Elasticsearch, but you have to set this up. But droid and machine are actually the same meaning, right? So if you want to run a semantic search, actually, you have to understand that semantic search is totally different than token and literal search that I presented just before. So that was the way we were doing things in Elasticsearch in the past. We are still doing that. It's still super performant, and we are doing still that. But we have introduced in like 4 years ago or 5 years ago something named vector search. So maybe you don't know, you know Elasticsearch, but Elasticsearch is also for vector search. What is a vector? Who knows this movie? Who is old as myself? Okay. Okay, so this is Airplane. I love this dumb movie. It's really dumb. I love it. So what is a vector? So a vector is a way to represent your data. So let's say that I want to index images here. So I have Leia on the left and Vader on the right. And here the characteristic I want to represent is this realistic or is this a cartoon? So Leia is totally realistic, so the coordinate is -1, and Darth Vader is a cartoon, so the coordinate is +1. Of course, you want to represent multiple dimensions. For example, is this picture a human representation or a machine representation? So Leia is definitely a human, so the coordinates are now -1 +1. Darth Vader cut in the half, so it's probably 0 here for the y-axis. So you have here his coordinates. And what we want to do is to gather together and group together the similar data. So let's add another one. So this is Luke now. Luke is totally realistic here, but he's missing a bit of his hand. So the value on the y-axis is 0.8. And then I have Obi-Wan Kenobi. Where is he? Oh, he's not showing it. Here, okay. And we have Obi-Wan Kenobi and then the machine. Okay. The goal of all that is to search. Let's say that I want to search for this image. What is the closest image that you think that should come first? What is it? The first image in our dataset. If I'm searching for Han Solo. Leia. Yes, indeed. Leia should be the first one. Who answered that? Who did answer? Raise your hand. You did? Okay. So probably you did some math. We will cover that in a moment. We'll see. The second one will be probably Luke. Yes, I guess. This is the closest after Leia. And then what do we have? I don't know, actually. I'm not sure who should I choose. But I choose here the Obi-Wan Kenobi, but it could be the machine. I think it's hard to decide. What I'm sure is that Darth Vader is at the opposite side of the things of Han Solo. That's the same thing for the text. When I was searching for, these are not the droids you are looking for, and those are the droids you are looking for, I expect to have those sentences at the opposite side as well. So, how do you index that into Elasticsearch? So, how do you index vectors, actually? So what you have to do is to take your input. It could be text. These are not the droids you are looking for. It could be images, or it could be audio. So I'm going to cover with the demo audio files, but whatever. You need to find a machine learning model. There is plenty of them on Hugging Face. The machine learning model I'm going to use is available on GitHub. I will share the link as well. And once you have the machine learning model you want to use, for example, for text, E5, Microsoft E5 is super nice if you want to use that one, specifically for different languages. For French, it works very well. For Portuguese, I think as well. So once you have your model, you transform the content from whatever source it is to a vector representation of the data. In Elasticsearch, it works that way. You create an index. So the index name here is e-commerce. You have a text field. So the description field is a text field. This is where you are running the old-fashioned, you remember the presentation with these are not the droids you are looking for, the analysis process. So this is what is happening within a text field. But I am also adding here a desk embedding field, which is the type dense vector. And this is where I'm going to index my vectors into Elasticsearch. So how I do that? If I want to index a simple text, as we used to do, we just posting the document to Elasticsearch using this API here to the e-commerce index. And you can see I have the description field with our best-selling, blah, 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 whatever text you have. So this is going to use the old-fashioned way, the analysis process I mentioned before. If you want to have a vector representation of your text, meaning with semantics or things like that, then you need to use the machine learning model that you found. You can use Python, you can use Java, you can use whatever language. There are plenty of libraries available. You can use Longchain if you want. Get the text, transform it with the model, and generate the embeddings. And the embeddings are exactly what you are seeing on the right in the yellow field, desk embedding. This is the vector representation of the same text that I mentioned before. That's the vector representation, which is coming from the machine learning model. And because you have images maybe as well in your dataset, you can use another machine learning model to generate a vector representation of the image, if you wish. So that's how it works. We have indexed data. How do you search now for vectors? So that's super similar. You are going to take the query that a user is typing, and you are going to use the same exact machine learning model that you used at index time. It needs to be the same one, the same machine model, the same machine learning model that you use at index time, and you are going to transform the query into a vector representation as well, with the meaning, etc. How do you do that in Elasticsearch? Let's say that you are going to search for summer clothes here. We are going to use what we call a KNN query in Elasticsearch. So we go through the same process that we saw previously, my Python process, and I'm generating a vector representation of summer clothes, which is what you see in green here on my slides. So this is the vector representation, and I'm searching using the KNN query on the field desk embedding, which is the dense vector field that I mentioned before. So this is the way we are doing vector search in Elasticsearch. The cool thing for you who knows already Elasticsearch is that you have access to all the other features of Elasticsearch. You can combine that with the BM25 search, so the lexical search that I presented before. The filtering, I don't want to have all the data set, but I know that in my e-commerce website, I'm on the woman part of the e-commerce website, so I don't need to get over data. I have pagination, aggregation, and all those things is available within the same query, so which is super cool. And then at the end, what you do, you take the vector representation, and Elasticsearch is going to compare that with all the vectors that you have indexed in the database before, right? And it's going to provide you ordered by score. So the closest vectors first are going to be provided to you. This is exactly what you did. If you remember the Han Solo demo, not demo, picture, you were doing something, you were putting the vector somewhere on the slide, and you say, okay, so the nearest neighbor is probably Leia first, and then Luke Skywalker. Exactly what Elasticsearch is doing. Of course, not only with 2 dimensions, but with many, many, many more dimensions, right? So how does it work? You did some math, I told you already. So what you did probably, you add this space where you have all your existing documents, so Leia and Luke here, and then you probably put Han Solo somewhere here in those 2 dimensions. And then you probably computed the angle. You did that? Yeah. And probably you computed the cosine. You did that, right? I'm sure. Actually, you did even more than that. You computed a score, which is 1 plus the cosinus divided by 2. This is exactly what you did mentally. You are not yet sure, but yes, you did that. So why you did that? Because for similar vectors where you have an angle which is close to 0, the cosine is close to 1. 1 plus 1 divided by 2 is close to 1. If you have orthogonal vectors, which is the case of Obi-Wan Kenobi, then the cosine is close to 0. 0 plus 1 divided by 2 equals 0.5. And then if you have opposite vectors, which is the case for Darth Vader, then the cosine is close to -1. And 1 minus 1 divided by 2 equals 0. Okay, so the score is between 0, opposite vectors, to 1, exactly merged vectors, I would say. Okay, so that's how it works behind the scene. Obviously, there is many more dimensions. It's not that easy as I can show here. There's more complexity in that, but you have the main idea of all that. I have to smile. Yeah. So, I love DJ. You want to dance, right? Yeah, exactly. So, okay, thank you. So that was me. Thank you. I was not saying thank you to get applause. I was just saying thank you for the video to stop, actually, but thank you so much. So this is my podcast, if you want to check it out. But that's a way for me to introduce the demo. So I have on my laptop some audio files, And those audio files are on the left here. I'm going to run a machine learning model on each audio file that I have on my laptop, and I'm going to generate the vector representation of my audio files. Exactly what I mentioned during the talk, right? With all those vectors, I'm going to store them in the best database ever, which is Elasticsearch. I'm based, of course, I work at Elastic, by the way. And then I'm going to hum a song. Actually, I have already something which is recorded. And with this sound, I'm going to use the same technique to get the vector representation of my sound, and then try with KNN search to find what is the closest sound that I have indexed in my database. So this is what I'm going to show. You will see the QR code again at the end. But yeah. Got it? Okay, cool. So let's do that. So I have a Python notebook here, so nothing super important here. I have installed some dependencies already, so one for Elasticsearch, obviously. And this one, the pan inference, is the important one. This is where the smart thing is happening. It's not in Elasticsearch. The model is coming from a third-party library. It's not in Elasticsearch. Elasticsearch is just helping me to find the closest vectors. That's all, right? It's doing that very well, but that's all. So I'm importing Elasticsearch, and here I'm importing this audio tagging, which is the machine learning model that I want to use. So here I'm loading the model, and this is where, again, all the smart part is going to happen. So I'm going to test the connection with Elasticsearch. Hopefully it will work. Yes, it works. So I'm running here in cloud because we have a cloud offer, so it's easier for me. But you can, if you check out the GitHub repository that I will share with you at the end, you will have access also to a local demo if you want to run that with Docker Compose. That's super easy. So I have here, I'm connected to Elasticsearch. And what I'm going to do, I'm going to create a new index. And in this index, I have my mappings. I have this audio embedding field, which is of type dense vector. Exactly what I mentioned. This is where I'm going to store the vector representation of the sound. And I can add, obviously, more data, so like metadata, the path, the timestamp, the title, the genre, whatever you have. So I have created my index. I have some script here. So this one is not important. It's just to list the audio files from my laptop. But let me execute. So this one is a script. I'm not running the script here. I'm just executing the function, so the function will be available later. So here, what I'm doing with this function, I want to get the embedding. So I want to get the vector representation of the sound from this sound file. Okay. So what I'm doing, I'm loading the sound, and then here, that's where all the magic is happening. I'm getting from my machine learning model the vector representation of the audio files. Okay? And then I'm returning that. And then to store into Elasticsearch it's super easy, exactly what I mentioned before. So you call the index API with the index name, and in the audio embedding field, I'm going to store the vector representation of my sound. Searching. How do I search? I'm calling the Elasticsearch again with the search method this time, and I'm running a KNN query, what I mentioned in the slide. Okay, nothing super important. I'm boosting here, by the way, the result by 100 because I want to have something like a percentage of match. That's just for me, but otherwise the score would be between 0 and 1. And then this is a small script to display the results. So let's start now. So let's list the audio files that I have. So those are, I don't have so many audio files. It's not about the performance of Elasticsearch or anything like that, but it's just a few of them. And what I'm doing for each file here, I'm getting the embeddings. So I'm generating for each file the vector representation of the sound. And then I'm storing that into Elasticsearch. And this is what you are seeing here. So this is the music I'm indexing. And here, you have the vector representation, one part of the vector representation. I think there are more than 700 dimensions here in my vector, but you have an idea. So those are floats which are sent into Elasticsearch. If you have seen the talk just before, you were mentioning quantization. So we are doing quantization automatically for you if you are sending floats. By default, we are doing integer on 8 bits quantization. And we can do even more now. We implemented for the first time in the world a paper, and we call that BBQ. It's not barbecue, but it's a better binary quantization where we can actually use bits to represent the vectors, which is even better. So let's search. So let's say that I want to search for this. Na 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 na. Okay, I'm not good at singing. I did my best. So this is me singing Bella Ciao, of course. So what can I do? I'm going to call this get embedding method with this audio file, this audio content. And then I'm going to send and call the KNN query that I mentioned before. Here. Okay. And then I'm going to display the results. Okay. So those are the 10 first results that I have. If you look at the first one, it's 99%. It's myself singing. It should be 100% because I should be equal to myself. But because of the binary quantization, not the binary, the quantization that we have behind the scene, I think that's why we don't have the exact similar value. At least that's the first one, and I want to skip this one because it's not useful for my use case. I'm most interested in the second one, as you can guess by the name. You know, is this one.
Na 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 na.
So much better than myself. So you can wonder, you say, oh, okay, he did Shazam or something like that. I'm going to give you an advice. Never trust a vendor. Like, I'm doing a vendor speech here, right? You need to understand, actually, what is the model I'm using? We never spoke about the model, what the model is doing, what kind of classification it is doing. So for my demo, it's working super well, right? But so let's explain the model a bit. If you go to the GitHub repository, you will see what kind of classification of the song is happening behind the scene. So here, what it's happening, is that a speech? Is that a male speaking, female speaking? Is that a baby? Is that someone laughing? Is that someone singing? Is that a male singing? Maybe it was me. Maybe somebody humming a song. Okay, that's the classification. It's not about notes. It's not about the tempo, the BPM, all those things. Not at all. It's just about the sound content. So do you have someone who is, I don't know what this word means, whatever. So is that an animal, a pig? I don't know. And then maybe what do we have? Oh, maybe we have some music, and musical instrument, guitar, electric guitar, bass guitar, etc., and drums, and whatever, trumpet, and all those things. Okay? So that's about the classification which is happening behind the scenes. So in my data set, I have another song with someone who is humming a song. So that's the reason we are super close together. It's not about the music itself. Right? So let's have a look at the second one. So it's still super close, not exactly as close. It's not about the music again, even though my demo makes you think that it's about the song, not at all the music. It's just someone who is doing a cappella with a bit of music in the background, so that's the reason it's happening here. And let's take the other one. So it's totally unrelated in terms of music, but we still have someone doing some a cappella with some drums, so that's the reason it's still popping up in the first position. It's not that close as the first one, but it's close enough. And then last one. So the first time I run this demo, I said, "Oh, I have the voice of an opera singer." And actually, no, sadly, no, it's not the case. What time is it? 12:10. I have to finish at 12 now. I have to finish now? Yeah, more or less, yeah. So that's cool because I think we are done. Okay, so you have the slides and the demo available here on my website if you want to check it out. And I will tweet on Blue Sky and LinkedIn and whatever about it. So thank you so much for attending this session. I hope you had fun. Thank you for having me, inviting me. That was a great pleasure to be in Faro for the first time with my girlfriend here. Hello, Laurence. So thank you so much and have a good day. And I forgot that I brought some stickers. So if you want to grab some stickers in the front row, then you can grab it. Questions? Oh, we have time. Okay. I could have run another set of demo then. Yeah. Yeah, let's go. Hey, come on, work. It's here, it's happening.
Hello. Yeah, so my question is, from the models that you have knowledge of, is there anything that would work like Shazam for humming?
I don't know yet. I wish I can find a model like this one, because for my own practice as a DJ, what I would like to do is to have my phone listen to a tune which I'm playing now, and the system should tell me, oh, maybe this one will be the next one, which is pretty much on the same tunes or vibes or anything like that. So I don't know yet. I think that Deezer has produced some very nice machine learning model. So Deezer is a French company like Spotify, but a very nice one. So I know that they have some models, but I did not try yet.
Okay, because it would be my life's objective to have one of those. So.
Yeah.
Anyway, thank you.
And I don't know how to train those models. I'm not a data scientist, so. Sure. Another question? Yeah. Front row.
Hello.
Hello.
I wanted to ask for the vector data search. If you have a data point that is kind of a mix of the two, how does it behave?
Like the one I had with Obi-Wan Kenobi and the robots in my demo?
For example, if you have a piece of music that in the middle it changes to a completely different genre, how does it behave? Which point would we choose?
So if the distance that we are computing is exactly the same, then probably it will try one and the other one just one after the other. The score will be the same. Mm-hmm. So you will have to choose as the end user with other characteristics. Like if you want to, for example, boost or combine the BPM value and add another score based on that, then you can do that. Okay. But that would be the idea.
Okay. Thank you.
You're welcome. Do we have one? Yeah.
Just a quick question. Is there any other type of parameter or search that you can do instead of KNN?
Yes. So instead of KNN is a way to do approximative search, if you wish. So it's super fast. If you want to exactly compute the cosine for every single vectors, then you can do that with a script in Elasticsearch. That's the way we were doing that before. It's super slow, right? That's the price to pay, but it will be super accurate. So normally what we are doing a combination of two. We first run a KNN query to just give, 100 vectors out of that, and then on those 100 vectors, we compute the cosine exactly. So that's the way. And we have multiple implementation. It's not always about cosines. Cosine is just about the angles, but we don't have the length of the vector. So you can do dot products if you want. So that's a setting that you put in the index for the field name. So you say, oh no, I don't want to compute cosine behind the scene, but dot product, and there are Euclidean distance and another one as well.
Okay, so combination to boost the performance.
Yes, exactly. Yeah,
Okay, thank you.
you're welcome. It's time for lunch? Yeah? Okay. I don't know. No, not yet? Okay, another?
Great talk.
Thank you.
I've used Elastic for years for text search, so it's a great tool, and I have no clue that it did vectors. So
Exactly,
thank
that's
you.
why I'm here.
Just out of curiosity, I'm checking the GitHub repo, and I see here that I can open this directly in Colab. So that was what you're showing, and the question is how to do it, because this will be helpful for my work.
So yes, you can open that in Colab. It will be able to execute the notebook from Colab, but you need still to provide Elasticsearch endpoint somewhere. So you can, because in Colab you cannot run Elasticsearch directly. So either you create one with cloud.elastic.co, you have 14 days for free, and you can create just a cluster with that. Or I think you can run Colab locally somehow and connect to your machine. So you can run a Docker Compose, start your Elasticsearch instance locally, and then ask Colab to connect to your local instance. That's how it will work.
Anyone?
You want to dance? Want to blah, blah, blah. Cool. Thank you.